Topic Notes 8.2 Marine Geology. This picture is the close-up of the backbone of Florida. It's limestone, and you can find it if you go to Winley Key State Park in the Florida Keys. This is down in one of their quarries. And if you haven't guessed it yet, you are looking at fossilized coral. Each of the Florida Keys is made out of this stuff, and basically, when sea levels were higher, these were thriving coral reefs. So today, we're going to talk about geology. The geologic features of the ocean floor are produced by the movement of tectonic plates and are shaped by erosional and biological processes. Now, Florida, because we are not close to a tectonic plate, a lot of our geological processes occur due to erosional, depositional, and biological processes. And of course, always check out those learning goals to make sure you know what you're expected to know after this set of notes. First, we're going to start with the concept of isostasy. And this is the process similar to buoyancy, but related to the Earth's crust floating on the flexible mantle. If you think about it this way, if you had a waterbed and somebody lays on that waterbed, the waterbed is going to give some, but you're not going to go all the way through because the water is going to buoy you up some as well. That's very much like what's happening with the lithosphere. Continents which are on continental crust versus oceanic crust are going to put a certain amount of pressure downward into the upper portion of the mantle, that is stenosphere, and that mantle is going to push back. And that kind of back and forth balancing act is what we call isostasy. Now, when we look at sea level, during the last ice age, the majority of the continental shelf regions were actually above water, which means our continents looked a lot larger because they were. Now, the continental shelf is right offshore of most continents, and it can be very wide, far away from the shoreline, or very close to the shoreline, depending on the structure. Now, how far underwater those shelves are, basically how deep, really depends on those changing sea levels and that melting and freezing of ice based on climate changes. And the second factor has to do with changes in land height as a result of isostatic changes. Basically, how thick the crust is. Is there a very thick layer of crust with very tall land, or is it very much minimal like the seafloor crust? So let's take a look at these continental margins a little bit more. So a continental margin is that submerged area right next to the continent, and it includes the continental shelf, which extends out, and it's usually relatively shallow. Then you have the continental slope, which is where you start going much deeper at a very high rate. And then the continental rise, which is sort of that really base of the slope as you go towards the abyssal plain. And that abyssal plain is the very flat area of ocean underneath. Basically, you have the difference between the continental crust and the oceanic crust. Now, for example, if you go up towards central and into northern Florida, the continental shelf extends quite a long way out to sea. This means that it's shallower for much farther out. Now, when I'm talking shallow, I'm not saying you can walk, but it might be 60, 80, 100 feet. Once you hit that continental slope, you're going to drop thousands of feet down. Now, here in West Palm Beach, we're actually at a point where the continental shelf is very close to us, and we also have the Gulf Stream running past. And so we actually get deep much quicker off of our coast. And of course, because that Gulf Stream is closer to us, we get that nice clear water, whereas if you travel into central and northern Florida, the water can be a little bit murkier. Now, we talked about plate tectonics, and we know that the Earth is constructed with a number of these large lithospheric plates and they interact along all of their margins. We also know that continents are not their own plates. Continents ride on larger lithospheric plates that contain oceanic seafloor as well. However, sometimes continents actually butt right up against the edge of their tectonic plate, and other times they don't. So the continents that are bordered by active plate boundaries we call active margins. An example of this is the west coast of South America, where basically you have the South American plate colliding with the Nazca plate. This forms a very deep trench right off of the coast as one plate, the Nazca plate, is subducting under the South American plate. It also contains volcanoes and earthquakes and that volcanic mountain range, the Andes. Now, of course, the continents that are not near an active plate boundary, very much like our own coast, are considered passive margins. I already mentioned the abyssal plain, and that is that relatively flat area of the ocean floor, usually between 3,000 and 6,000 meters deep, that extend away from the continental shelf. Now, 50% of the Earth's surface actually includes the abyssal plain. Now, when you go down in submersibles and you look at the seafloor in the abyssal plain, it looks relatively flat. In reality, it's a jumble and uneven, rocky sort of terrain. However, over years and years and years, all of the small decomposing organic matter, usually of calcium carbonate or siliceous origins, are going to fall down onto that seafloor and start to cover up all of that kind of uneven rockiness into this one sort of pale white layer. And so it makes it look very flat. And of course, you get a gentle rise as you head towards mid-ocean ridges. Hopefully by now you've realized that mid-ocean ridges occur at divergent boundaries where the plates are pulling apart. And when that happens, new molten material from the mantle is going to push up onto the seafloor and start to create new crust, and usually forming these large mountain chains across the mid-ocean ridges. Now, there generally is a central rift valley, which occurs at the center of the ridge where the plates are pulling apart. In 1977, we discovered something interesting. At the mid-ocean ridges, and this was actually found first off the coast of Galapagos in the Galapagos Rift, there are what we call hydrothermal vents. Now, these vents occur in relatively deep water, typically over 2,000 meters, but they represent an oasis of life in a normally very low diversity zone, which is the deep sea. Hydrothermal vents occur generally because of the underlying magma near the mid-ocean ridge. Cold ocean water seeps down into the cracks and crevices as the mid-ocean ridges are pushing apart. And as it gets closer to that heated magma chamber, the water begins to superheat. From there, the water is going to shoot up towards the surface and the open water. Now remember, water is the universal solvent. So as this superheated water is racing through the rock cracks, it's going to dissolve a lot of the minerals it finds there, things like iron and copper and zinc and sulfur. Now that superheated water is going to escape through fissures in the rock, meeting that freezing ocean water. The minerals with that decrease in temperature are going to precipitate out of the water, forming solids again, and eventually stacking up and forming these large chimney-like structures. We often refer to them as black smokers because as the water's pouring out of these chimneys, it looks black because of all the dissolved materials in the water. Now, although hydrothermal vents are typically found along mid-ocean ridges, we have located them in other geologically active areas as well. Now, the seafloor is generally composed of basaltic rock that really is formed at mid-ocean ridges. But like I mentioned before, there are layers and layers of sediment that generally fall on this basaltic rock, and you don't always see it. Now, just a quick rundown of marine sediments. Now, sediments are defined by their size and composition. There are quite a few categories of size, but we'll stick with some basics. Silt being the finest, then we got fine sand, and then coarse sand, and then gravel, which would be kind of like little small stones. Now we can talk about composition. Now, marine sediments can be separated into several different categories of compositions. First, we have hydrogenous sediments. These were formed from seawater through chemical processes. This includes things like carbonate, phosphorites, and manganese nodules. Manganese nodules actually have some economic value, especially as a metal. They're often found as little balls of rock scattered across the ocean floor. Then we have biogenous sediments. These are sediments from living organisms. So we're talking things like crushed coral, mollusk shells that have gotten busted apart, plankton exoskeletons of shells that fall down onto the seafloor after they've died. And the deep sea is almost completely composed of the remains of plankton and biogenous sediments. Then you have lithogenous sediments. And as the name might suggest, lithosphere, lithogenous, this is material that's coming from land. It's coming from the continents. And usually it's from rock that's eroded through wind and water, freezing and thawing, those sorts of processes. These particles are then carried from the land by water into the sea and are found a lot of times across the continental shelves. Okay, that brings us to our in depth question. What type of sediments might you find along the Palm Beach County beaches? Think about composition. We just talked about three major categories. Are you going to find one or multiple of those types of compositional categories? What about some of the sizes? Let me know. And of course, until next time, keep thinking.